Ladies and gentlemen, good morning and welcome to MFTG. Today I would like to share with you some of the recent progress in meaningful type game theory, that's MFTG. The agenda now in the next couple of minutes is to describe you a class of MFTG with a random number of interacting agents, interacting decision makers, interacting players. And we show how we could solve this category of games, in particular using learning algorithms, distributed learning algorithms, coalitional learning algorithms, cooperative learning algorithms. So here is the setup. The first thing is we consider atomic and non-atomic decision makers. Atomic decision maker means in terms of influence in the state dynamics and in the pair function, this player is contributing through his own action, own state, right? And it's going to be important, non-negligible in terms of effect. A non-atomic decision maker has his contribution, but his a single contribution has no effect or negligible effect in the pair function or in the state dynamics, right? Of course, he has an effect in his own state, but not in terms of pair function, right? In terms of consequences, right? So this can be captured through the empirical measure, for example, when the number of agents is large. But if you have finite number of agents, then still 1 over n and being the size of the number of players is still non-negligible, right? So that's the thing here. We consider atomic and non-atomic players as meaningful type game theory allow to do that, and the atomic players they have their own state, own distribution of state, own action, own distribution of action. These are non-negligible in the state dynamics and in the pair function. Now the non-atomic agents, they are selected generically. They have no effect in the population mean field, but of course they have an effect in their own individual mean field, which is the state of own, the distribution of own state and this distribution of own action, right? So we consider this class of games, and we want to solve the manifold type equilibria. We want to find the solutions, right, of using concept. For example, hierarchical solutions could be, Stackelberg solutions could be risk-sensitive solutions, could be mean variance solutions, and so on and so forth, right? So we want to find a solution concept there, and especially we want to use learning algorithms to find this class of solutions. So the idea here is to develop learning algorithms. So learning manifold type equilibria, whatever the solution concept behind the equilibrium is, right? Birch equilibrium, mutual support, competitive equilibrium, and so on and so forth. So the first class of learning algorithms that we consider is the class of gradient descent method, ascent methods. So these are when the pair functional is regular enough, means you could do some variations on differentiations and so on. But in the case where it is not necessarily differentiable, you look at when it is measurable, means you could have some numbers you could measure, you could evaluate at some point, and then you could do finite differences and how they behave. So if it's not measurable at all, then you might go beyond. You could do estimations through expert opinions, statistics, survey, and so on. So that will be interval based. So the payoff belongs to an interval with some probability and so on. You want to estimate those probabilities, right? So then you look at satisfactory solutions for a set is satisfactory if the probability of being in that set is above a certain threshold or so. You could define a notion of satisfaction there and then estimate and then learning. So the first class of learning is this descent, and then if descent is not possible, you do estimations to do another kind of descent. For example, perturbation techniques, sign techniques, and estimation of uncertainty set, and so on. So these are the first category. Second category is going to be distributed learning through the reinforcement learning, the reinforcement based algorithms, and evolutionary. The third one is going to be evolutionary algorithms, so population based dynamics, and evolutionary game dynamics, and so on. So you could if the action set is continuous, you could do that. If the action is discrete, you could do that as well. Now you could go beyond that. You can have swarm based learning, you can have neural network based learning, and you can have in particular distributionally robust GAN, distributional robust generative adversarial network. But the difference here is that since you have atomic and non-atomic games, so you might have multiple classes, and each of the players has its own learning dynamics. Imagine that you get individual learning dynamics for each of those individual learners. Then you might get a hierarchy of distributionally robust generative adversarial network, right? So you get a network of network, and then learning algorithms for each of those items. You can get a learning of learning. So you might have, for example, if you are using a framework of deep learning, you get a learning of learning in that. So this is really a very interesting class of systems that we want to study. This is what I wanted to share with you today. Thanks for your time, thanks for your attention, and see you soon on MFTG. Bye.